We're in Rosen, Discrete Mathematics and its Applications, section 10.4 on graph connectiveness. We've studied uh, paths in graphs and connectedness in graphs. We're going to link it back to the concept of graph isomorphism. So let's look at an example of two graphs and let's see if they're isomorphic. Here we have two graphs that have 6 vertices each. 4 vertices of degree 3 in each, 2 vertices of degree 2 in each, and there are 8 edges in each. Are they isomorphic? It turns out that they are not, because if we'll notice on graph H, we have a circuit of length 3, but in graph G, there is no circuit of length 3, so they would not be isomorphic. And we're going to look at ways to look at paths and circuits to detect that. Graph 7, figure 7 with graphs G and H, are they isomorphic? Well, here I have a cycle of length 3, and in H and G I have a cycle of length 3. I also have a cycle of length 4 by those marked, I marked one of them twice, those marked edges. And I also have a cycle of length 5 if I go to this edge first and do that. So 1, 2, 3, 4, 5. Yep. All right. So it turns out that there is a way to make an isomorphism between these two graphs, and you can see it more readily if you can imagine drawing this, taking this U and dragging it over to here, and then you could rotate it and find a very visual isomorphism. And then you can remember that these are not isomorphic. And this one's harder to tell with circuits because there are circuits of length 4, there's circuits of length 6, there's circuits of length 8. But it turns out that the circuit of length 8 in G has to revisit vertices, whereas the circuit of length 8 in H can go through each vertex only once, and that's not true in G. So they're another way to show that that is not isomorphic. Well, let's capture a very important theorem about paths between vertices, and we'll use the adjacency matrix to do that. And here's the theorem, is that if you have an adjacency matrix on a graph G with our vertex ordering V1 through N, the number of different paths of length R from Vi to Vj for R greater than 0, that's what we need for a path length, is equal to the ijth entry of the A matrix raised to the R power. And we'll do a proof of that by mathematical induction. The basis step, paths of length 1, are the ij entry of A, which is A raised to the 1 power. And that's the definition of the adjacency matrix, is which vertices have edges between them, and an edge contributes 1 to the path length. Our inductive step will assume that the ij entry of A raised to the R power is a number of different paths of length R from Vi to Vj. And now if we multiply A to the R times A, we get A to the R plus 1, and it has entries it has entries at ik of AI1 plus BI1 plus A1j and BI2 plus A2j, basically the definition of matrix multiplication. But by the inductive hypothesis, each of these BIKs is the number of paths of length R from Vi to Vk. Well, the paths of length R plus 1 from Vi to Vj can be thought of as made up of paths of length R from Vi to some Vk, and then that last edge from Vk to Vj. So by the product rule for counting, the number of such paths from length r to bk is bik. That's our inductive hypothesis. And the number of edges from vk to vj, 1 if it's a simple graph, it could be more than 1 in a multigraph. That's equal to bi1 times a1j all the way out to bin times anj, which is precisely the ij entry of a r plus 1. So it's a very handy tool to be able to raise a to a power to get the number of paths of length of that power between two vertices. Now let's apply it to this graph here. Here's G in the adjacency matrix, the paths of length 1 between our vertices. I want to know how many paths there are of length 4 from A to D. Well, in order to do that, I'll take A and raise it to the 4th power. And I look for the 1, 4 entry. So this is A, this is D, so I'll be looking at that. There's 8 paths of length 4 from A to D. Well, what's one of them? I could go A, C, D, C, D would be one path of length 4. I could do A, D, B, D, another path of length 4. And we've got them enumerated right here. So you can trace all those out and see that there's 8 possible ways to get from A to D in 4 steps. Another application of this is to graph isomorphisms. Let's go back to our 2 graphs, one with a circuit of length 3, one that we said did not have one. Well, some graphs are very complicated. What if it's hard to tell if it has a circuit of a certain length? We can just take its adjacency matrix and raise it to a power. If we're looking at the adjacency matrix of G and H, it's hard to tell from that they're not isomorphic. They have the same numbers of 1s and 0s. If I raise it to the power of 2, square the matrix, I do have some 1s resident in my adjacency in the resulting matrix for H, and no 1s in the resulting matrix for G, but and so I could conclude right away that they're not going to be isomorphic. But if I'm worried about circuits, I want to be looking along the diagonal, and you can see that the diagonals in these cases are the same. So the number of paths of length 2 back to each vertex is the same. But now if we raise it 1 more power to get the adjacency matrix to the 3rd power, now I see that for G there were indeed no paths of circuits of length 3, and that there were circuits of length 3 in H. Alright, so that is the use of the adjacency matrix and raising it to powers to count paths between vertices and to investigate isomorphisms.